Welcome back to Vijay Academy. Please subscribe to my channel and click on the bell icon for receiving the notifications of the new videos. So in this video, I'll be explaining exercise 1.2 from real numbers. So the question is like this: express each number as a product of its prime factors. So we have to write the prime factorization of 140. So before that, let us know what is the meaning of prime numbers. So prime numbers are the numbers having only two factors. The numbers like 2, 3, 5, 7, 11, 13, etc. Such numbers are called as prime numbers because these numbers have only two factors. Like for example 2. 2, the factors of 2 are 1 and 2. The factors of 3 are 1 and 3. The factors of 5 are 1 and 5. So these numbers have only two factors. Such numbers are called as prime numbers. So here we need to divide the given number only by the prime numbers so that we get the prime factorization of the given number. So the first number is 140. Let us divide 140 by only prime numbers. So the smallest prime number that can divide 140 is 2. So let us divide this by 2. So 140 is divisible by 2 for 70 times, and then again 70 is divisible by 2 and for 35 times, and 35 is divisible by 5 for 7 times, and 7 is a prime number. So we stop the division here and write 140 as the product of its prime factors, that can be written as 2 square into 5 into 7. So next question is 156. So divide 156 only by the prime numbers. So 156 is divisible by 2. For 2 sevens are 14, 1 is the remainder. So 2 eights are 16. 78 is also divisible by 2. 7 threes are 6 and 1 remainder. So it becomes 18. 2 nines are 18. So 39 is divisible by 3. 3 ones are 3 and 3 threes are 9. So 13 times. 13 is a prime number. So the prime factorization of 156 is 2 square into 3 into 13. Next we have 3825. So number 3825 is ending with 5. So let us divide this directly by 5. So it is not necessarily to divide only from the smallest prime numbers. You can divide the given number by any prime number. You can start in any order. You can divide it, but we should divide it only by the prime numbers. So 3825 is ending with 5. So let us divide this by 5 directly. So 5 sevens are 35. So 3 is the remainder. So it becomes 32. And 5 6 is 30. 2 is the remainder. It becomes 25. 5 5 is 25. And next 765 also is divisible by 5. So let us divide this by 5. 5 ones are 5 and 7 minus 5 is 2. So we get 26, and 5 5 is 25. 1 is the remainder, so it becomes 15. So 5 3 is 15. So we get 153. 153 is divisible by 3. So now we get 153 is divisible by 3 for how many times? 3 5s are 15 and 3 1s are 3. So it is divisible for 51 times. 51 also is divisible by 3. So again dividing this by 3, 3 ones are 3 and 2 is the remainder, we get 21, and 3 sevens are 21. So 17 is the prime number. So the prime factorization of 3825 is 3 square into 5 square into 17. So the next question is 5005. So again we can divide 5005 by 5. It is when you divide this by 5, 5 ones are 5 and take 0. 0 is not divisible by 5. Take next digit. So when you take next digit, put 0 in the quotient column. And now still it is not divisible. 0 0 is not divisible by 5. So include one more digit. So now before you include the next digit, put one more 0, and now it is 5. So 5 is divisible by 5 for one time. So it's for one time. So now it is divisible by which prime number we have to check. So 1001 is not divisible by 2 as well as 3 and 5. So next number is 7. Let us check whether it is divisible by 7 or not. So we have the divisibility test for 7, that is double the last digit, so that is 2 ones are 2, and then subtract it from the number formed by remaining digits, that is 100. So 100 minus 2 is 98. So if the difference between the double of the last digit and the number formed by remaining digits, the difference of these two is a multiple of 7, then the given number is multiple of 7. So 98 is divisible by 7, so therefore 1001 also is divisible by 7. So let us divide this by 7. So 7 ones are 7, 3 is the remainder, we get 30, and 7 fours are 28, 2 remainder 21, 7 threes are 21. Now we get 143. So let us check whether this 143 is divisible by 7 or not. So till now we have divided. Now see, when we are dividing 5005 and 1007, 1001, these numbers were not divisible by 2, 3, 2 and 3. So 143 also will not be divisible by 2 and 3. So we need to check only the number above 7, because till here we have tried with 2, 3, 5 and 7. Now we need to check only by 7 and above. So now the next prime number, first let us check whether it is divisible by 7 or not. 143 is not divisible by 7. Then we check this by 11. We know the divisibility test for 11. So add the digits in the odd places. Add the digits in the odd places. So 1 plus 3 is 4. And add the digits in the even places and find the difference between them. So if the difference is either 0 or a multiple of 11, then it is divisible by 11. So we got the difference 0 here. So 143 is divisible by 11. So dividing this by 11, it is divisible for 13 times. So we get the prime number 13. So the prime factorization of 5005 equals to 5 into 7 into 11 into 13. So next we have a number 7429. So 7429, whether 7429 is divisible by 3 or not, let us check. Since it is an odd number, 7429 is an odd number, not divisible by 2. Check for 3, it is not divisible by 3 also. It is not divisible by 5 also, because it is not ending with 5. Now let us check this for 7. So double the last digit, 9. 9 twos are 18, and subtract it from the number formed by remaining digits, that is 742. So 12 minus 8 is 4, and 3 minus 1 is 2, and 724 we get. And still it is a bigger number. Apply the same process for 724 also. Double the last digit, you get 8, and subtract it from the number formed by remaining digits, that is 72. 72 minus 8, 12 minus 8 is 4, and 64. 64 is not divisible by 7, therefore 7429 is not divisible by 7. So the next prime number is 11. So apply the divisibility test for 11. So add the digits in the odd places, that is 7 plus 2 9, and add the digits in the even places, that is 4 and 9 13. So the difference between 9 and 13, the difference between 9 and 13 is 4. It is neither 0 nor a multiple of 11, therefore the given number is not divisible by 11 also. Next we need to check this by 13. So we need to divide this directly by 13 and check whether it is divisible by 13 or not. So if you divide this by 13, you will come to know that it is not divisible by 13. So next we need to check with the next prime number 17. So it is divisible by 17. So you need to check whether it is divisible by 17 or not, and then you should divide it. So it is divisible by 17. So 17 3s are 51, 17 4s are 68, 17 4s are 68. So the remainder will be 6. So you get 62. So 17 3s are 51. So the remainder will be 11. So we get 119. 119 is divisible by 17 for 7 times. So we get 437. Now 7429 was not divisible by any prime number other than 17. So now 437 also will not be divisible by any prime number less than 17, because we have already tried the prime numbers less than 17 for 7429. It was not divisible, so we need to go for 17 or the number bigger than 17. So 437, you need to check 437 is divisible by 17 or not. It is not divisible by 17. Then you should check with this 19. So it is divisible by 19. So it is divisible by 19 for 23 times. So 23 is a prime number. Therefore, the prime factorization of 7429 is 17 into 19 into 23. So next we have second question. Find the LCM and HCF of the following pair of integers and verify that LCM into HCF equals to product of the two numbers. So the first question is 26 and 91. So let us write the prime factorization of 26. So the prime factorization of 26 is divisible by 2 for 13 times. So 26 can be written as 2 into 13. Next, the prime factorization of 91. 91 is divisible by 7. So 7, 1 is a 7 and 2 is a remainder, 21 you get. 7 3 is a 13, 7 3 is a 21. So the prime factorization of 91 is 7 into 13. So first write the prime factorization of both the numbers given, and then we need to find the HCF and LCM. So we know the product, we know the meaning of HCF, that is highest common factor. We get the highest common factor when you multiply only the common factors with their least powers. So by multiplying only the common factors from both the factorizations with the least powers, with their least power, we get the HCF. So in this we have only 13 as the common factor, and now the least power of 13 is 13 itself. So that is 1, 13 power 1. So we should take it as 13 itself. So HCF is 13. If we have more than one common factor, then we should write both the common factors here and then multiply them to get the HCF. Now LCM. LCM is the product of all the factors with their highest powers. So here all the factors present in both the factorizations are 2, 7 and 13. And in each case their highest power is 1 itself. So the numbers that we should write here is 2, 7 and 13 itself. And multiply them. So 2 7s are 14 and 14 into 13 multiplying 14 and 13 we get 182. So the LCM of these two numbers is 182. Now let us verify the relation given here, that is LCM into HCM. First let me multiply LCM and HCF of these two numbers. LCM is 182 and HCF is 13. So on multiplying 182 and 13 we get 2366. And let us multiply the given numbers now, the product of the numbers, product of two numbers that are 26 and 91. So on multiplying 26 and 91 we get 2366. So hence we can write that it's verified. Hence the relation is verified. So we have the next question, that is 510 and 92. So first let us write the prime factorization of both the numbers. So the prime factorization of 510 is, so we should divide this 510 using prime numbers and then we should write it. So when we divide 510 we get the prime factors 2, 3, 5 and 17. And the prime factorization of 92, dividing 92 we get 2, 2 into 23. So now let us find the HCF of this. As we know, HCF is the product of only common factors with their least powers. So let me write this in the exponential form. The first one will remain same when you write the prime factorization in the exponential form. When you write the prime factorization for 92, this can be written as 2 square into 23. And now look at the common factors. So we have the common factors only, that is 2. 2 is the common factor in both the prime factorizations. So we write 2 here, and whose least power is 2 power 1. So we should write 2 itself. So HCF is 2. Now let us find the LCM. LCM is the product of all factors. So let me write all possible factors present here. That is 2, 3, 5, 17 and 23 with their highest powers. So 3, 5, 17 and 23, each of them will have the highest power 1 itself, whereas 2 has the highest power 2. So we should write 2 square and multiply all these numbers. We get the LCM 23460. We get 23460. So now you can verify the relation, that is HCF into LCM. HCF into LCM, that is 2 into 23460, which will be 2 into 0, 2 6 are 12 and 2 4 are 8 plus 1 9 and 2 3 are 6 and 2 2 are 4. You get 46920, and multiplying the numbers, the product of two numbers, which is 510 and 92, product of numbers which is equal to 510 into 92, so whose product also will be same as 46920. So then you can write, hence the relation is verified. Similarly, the third question, that is 336 and 54. So divide 336 and 54 using only prime numbers and then write the prime factorization of 336 and 54. The prime factorization of 336 is 2 raised to the power 4 into 3 into 7, and the prime factorization of 54 is 2 into 3 square. Now the HCF, it is the product of only common factors with their least powers. So the common factors from these factorizations are 2 and 3. So let me write 2 and 3. Now let me take the least power of 2 in the case of 2 as well as the least power in the case of 3. So in each case the least powers are 1 itself. So we need to write this as 2 and 3 itself. So we get the HCF 6. Now LCM. LCM is the product of all factors. So here 2, 3 and 7 are the all factors. So now the highest power for 2 is 2 power 4. The highest power for 3 is 3 square and 7 will remain same. So on multiplying these numbers we get 3024. On verify, now let us verify the relation, that is HCF into LCM. HCF is 6, LCM is 3024. Multiplying these two numbers, that is HCF and LCM, we get 18144. And also the product of two numbers, we get, that is 336 and 54, whose product also will be 18144. Therefore you can write, hence the relation is verified. Next we have question number 3. Find the LCM and HCF of the following integers by applying the prime factorization method. So the same method we should follow here. So first let us write the prime factorization of 12, 15 and 21. So the prime factorization of 12 is 2 square into 3, and the prime factorization of 15 is 3 into 5, and the prime factorization of 21 is 3 into 7. Now HCF equals to the only common factor. So in this we have only one common factor, 3, with the least power 1. So 3 itself is the answer. Now LCM is the product of all factors. So that is 2 into 3 into 5 into 7. Now the highest power of each of these factors we must write. So in that case we get 2 square here, and all other numbers will remain same, that is 3, 5 and 7, and whose product is 420. So now for three numbers, the relation between HCF and LCM is not applicable. So we need to just find the HCF and LCM in this question. So next one, question number 2, we have 17, 23 and 29. So we need to find the prime factorization of each of these numbers. So but we cannot write the prime factorization of each of these numbers because these numbers are prime numbers. So the HCF of all the prime numbers, the HCF of all the prime numbers is 1. Since all the three numbers are prime, whose HCF will be 1 because they do not have any common factor. Whereas LCM, it is the product of all the prime numbers, 17 into 23 into 29. So by multiplying these three prime numbers, we get 1, 1, 3, 3, 9. Next question. So 8, 9 and 25. So the prime factorization of 8 is 2 cubed. The prime factorization of 9 is 3 square. The prime factorization of 25 is 5 square. Now HCF. There is no common factor from each of these factorizations. So HCF is 1 and LCM. So here again write all factors with their highest powers. So that is 2 cubed into 3 squared and 5 squared. So whose product is, the product of these three numbers is 1800. Next, question number 4. So HCF of two numbers is given and we need to find the LCM of two numbers. So here HCF and the two numbers are given. We are supposed to find the LCM. So let us use the relation between the numbers. So the relation is HCF into LCM of two numbers equals to the product of the two numbers. So let me take the product of the two numbers as A and B, that is A into B. So now let me substitute all the values here. So HCF is given, which is 9, and we need to find the LCM. So write this as it is, and the two numbers are 306 and 657. Transpose 9 to RHS. So we get LCM equals to 306 into 657 divided by 9. Now 306 is divisible by 9. 9 ones are 9 and 9 threes are 27, 3 carry 36, then 9 fours are 36. So finally we get 34 into 657, whose product is 22338. So next question is, check whether 6 power n can end with the digit 0 for any natural number n. So here it's very simple. Any number end with 0 which is divisible by 2 and 5. Any number end with 0 which will be divisible by 2 and 5. But in the prime factorization of 6, we do not have 2 and 5. So as when you write the answer, first you can write that any number end with 0 if it is divisible by 2 and 5, if it is divisible by 2 and 5. But the prime factorization of 6 power n is 2 into 3 whole raised to the power n. So the prime factorization of 6 do not contain both 2 and 5. It has contained only 2. It does not contain 5. So this number will not end with 0 for any value of n. So it's very simple. We can just write that it can be absorbed that 5 is not in the prime factorization of 6 power n. 5 is not in the prime factorization of 6 power n. Therefore for any value of n, 6 power n will not be divisible by 5. 6 power n will not be divisible by 5. Therefore it does not end with 0. Therefore it does not end with 0. So when you get a question similar to this, you need to just check that in the prime factorization of the given number whether 2 and 5 is there or not. If the prime factorization of any number contain 2 and 5, then it will end with 0 for any value of n, otherwise it will not end with 0 for any value of n. Next question, explain why 7, 11, 13 plus 13 and another number are composite numbers. So it's very simple. In 7, 11, 7 into 11 into 13 plus 13. So we need to just show that this particular number has more than, it has more than 2 factors. We need to just show that it has more than 2 factors. So in 7 into 11 into 13 plus 13, we can take 13 as common factor, and then we get 77 from the first number. When you take 13 as common factor, divide 7 into 11 into 13 by 13, we get the quotient 77, and divide 13 by 13, we get the quotient 1. So now this can be written as 13 into 78. So this number can be factorized into 13 into 78. So this particular number is divisible by 13 as well as 78, and we know that every number is divisible by 1 also. So from this we got to know that this particular number 7 into 11 into 13 plus 13 is divisible by more than 2 numbers. That means it has more than 2 factors, that is 13, 78 and 1 also. So we can directly write that 7 into 11 into 13 plus 13 is a composite number. So for the other number also you must do in the same method. Please try that by yourself. So question number 7. There is a circular path around a sports field. Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again at the starting point? So when they are taking rounds, in a circular path, Sonia takes 18 minutes and Ravi takes 12 minutes to complete one round. But after how many minutes they will meet at the same point, at the starting point? So to find after what time they will meet again, it's very simple. So we need to take the multiples of 18 and 12. So the multiples of 18 is 18, 36, 54, etc. Similarly 12, 24, 36, etc. This is one way of finding. If you want to use the prime factorization method, it is the least common multiple. It is the least common multiple of 12 and 18. At that particular time they will meet again at the starting point. So just write the prime factorization of 18. So that is 2 into 3 square, and the prime factorization of 12, that is 2 square into 3. So now the LCM of these two numbers is equal to 2 into 3, means let me write all the factors here, that is 2 and 3, and with their highest powers. So 2 square into 3 square, so which is 36. So they both will meet again at the starting point after 36 minutes. So you can write the statement that after 36 minutes, they will meet again at the starting point. So thank you for watching the video, and please share this video with all your friends. It will be very useful for them. Thank you so much.